talk about an idea that's very useful for Newton's first and second law of motion, the idea of a free body diagram. We're going to talk about equilibrium. Equilibrium in the sense of physics, not like chemical equilibrium. So go through the wording here and then make sure you understand what all the words mean. So I have some object, and for now, we're just going to talk about rigid bodies. Rigid body means, let's say it's a plate. I put two dots on the plate to mark two positions. If the plate is rigid, then no matter how I rotate, spin, translate, whatever I do to it, those two dots keep the same distance relative to one another if the object is rigid. If the object's deformable, like it was like a sheet of putty, then obviously I put the two dots on it and I pull the sheet of the putty or I squish it, then that distance is going to change. So it's not rigid. So a rigid body is an approximation. Nothing that is perfectly rigid, because that would violate causality. But there are many things that, to a good enough approximation, they are rigid bodies. So let's imagine I have a rigid body and all the parts of the body are going to move in the same way. For now, what we're going to do for a rigid body like that is just represent it as a single dot. That's what this dot is. We are good physicists and we have drawn our choice of coordinate system. So X goes to the right, Y goes up the page, and there's like a tug of war happening with this object. So person one is pulling to the right and up, person two is pulling to the left, and person three is pulling down. So in this three-way tug of war, those are the forces that are acting on the object. And that's the idea of a free body diagram. When we talk about torques, we're going to have to be a little bit more careful and have like an extended object because it matters where the force is applied. But for right now, first pass at this free body diagram for a car, for Superman, for an airplane, for my chair, for me, for anything. The object is just a dot. And then we just fill in all the forces that act on the object. Normally, an object on Earth is going to have Earth's gravitational pull pulling it down. I'm not falling through my chair right now, so there must be some force that is opposing my weight, which is a normal force coming from the chair, and we're going to meet all these forces, at least as a first pass in chapter 5. Then from your free body diagram, once you have drawn out as vectors all the forces acting on an object, then you can add those forces together through the principle of superposition, right? That just means that like the strength of force 1 doesn't depend on 2, and 2 doesn't depend on 3, and 1 doesn't depend upon 3, and so forth, right? So the forces are what they are. I just add them together as vectors, and either we sum up to 0, in which case the velocity of this object is constant, or they don't add sum to 0 as vectors, and then the direction of the net force is going to tell me the direction of the object accelerates. So this is a sort of the warm-up step when we're going to apply Newton's first law or Newton's second law. And keep in mind, I could have Newton's first law hold in one spatial dimension, but Newton's second law hold in a perpendicular direction. You can mix and match. All right. If we happen to have the net force on an object add up to 0 as a vector, that means the acceleration is 0, which means that the velocity of the object is constant. And there are two types of equilibrium that emerge out of this. Right. So first off, if the net force on an object is 0, the object is in equilibrium. Okay. That equilibrium could be static, so its velocity remains constant and its initial velocity was 0. So that's the wording you might be more familiar with. An object at rest begins and remains at rest unless acted upon by an outside force. That's the case of static equilibrium, but that's not the only thing that can happen with Newton's first law of motion. If the object is in motion and in equilibrium, it will continue to move with a constant velocity, and that's the idea of dynamic equilibrium. Okay? So we have lots of nice straight flat roads in Indiana. If you're going down such a straight flat road at a constant speed and you're at a constant velocity, that means I add up all the forces that are acting on your car, they have to all add up to zero. Okay? That's a case of dynamic equilibrium. All right. Let's try a question. If an object is moving, can you conclude that there are forces acting on it? If an object is at rest, can you conclude there are no forces acting on it? Consider each of the following situations. In which one of the following cases, if any, are there no forces acting on the object? A bolt coming loose from its satellite orbits the Earth at a constant speed. After a gust of wind has blown through a tree, an apple falls to the ground. So perhaps that was going to bonk Isaac Newton upside the head. A man rests by leaning against a tall building in downtown Dallas. Sometime after a parachute opened, the skydiver fell toward the ground at a constant velocity. Or forces are acting on all the objects in choices A, B, C, and D. Think about which one you think is correct, and then compare with your physics friends. And then when you're ready to go over the answer, you can unpause the video. All right, there are forces acting in all of those cases, A through D. So even though the object is, the bolt is moving at a constant speed, it's moving in an orbit. So the direction of its motion is changing. That's caused by the force of Earth's gravity. Apple falls to the ground, force gravity. Man rests by leaning against a tall building in downtown Dallas. So the person has weight straight down. There's a normal force exerted by the sidewalk onto the person. The person is leaning against the building. So I'd say force against the building, and the building pushes back on the person, where the force is equal and opposite. So a whole bunch of forces there, even in Dallas. And then falling to the ground at a constant velocity, the velocity is constant because the net force is zero, not because there are no forces. Person, she still has gravity pulling her down, but that is being canceled out by a force of air drag on her parachute. So all of those cases are cases where there are forces acting.